Next, I'll be reviewing using a kinematics table with inertial frame and comparing it to body fixed. Here we have a link that's pinned at B. I show it in two positions on the left and the right, is pinned at B, and from B to P, it can extend. So it might be a pneumatic cylinder, hydraulic cylinder, a slot, but something that can move in a radial direction. So we see R1, that length is a function of time, as well as theta, of course, is a function of time. Now, if we zoom in on our nomenclature, inertial we think of as fixed to the Earth, and if our axes are typically x, y, z, small x, small y, small z, our unit vectors would be small I, j, and k. If it was capital X, Y, Z, it would be capital I, J, K. What happens is, as you do multi-body problems, it gets difficult if you stick with X, Y, Z. Sometimes they use prime notations, double prime. So typically what we do is, for the one that's really truly fixed to the Earth, and you might be doing a problem where the Earth rotates, but let's not worry about that for this mechanisms class. For each body, you'll need its own coordinate system. So if I leave IJK for fixed to the Earth, I can introduce a body fixed coordinate system that moves with the link. The axes, if we call them B1, B2, B3, would have a unit vector B1, B2, B3. The next one we'll see will be a C-frame. So axes C1, C2, C3, and then C1 hat, C2, C3 hat, right, would be your unit vectors. It keeps things simple. So I've drawn it in two positions. So I have this position here, and then I drew it here just to show both it rotating, it's stretching, as point P is further away from B, so R1 is longer. But if you see, I is still to the right, J is still up. And yet B1 moves along with the link or the mechanism, as well as B2, which is orthogonal, right? So 90 degrees apart. So just, we spent some time on that in class, and again, any problems with that might be handy to draw it in SolidWorks, make a model, or come see one of your faculty. So let's do a quick comparison, and then I think in the next video, I'll do one where the base B moves either left and right or up and down. So I'm working on a comparison here that drawing at the top, either of those two drawings on the top, I tend to use the one on the left more, would apply to either of these kinematics tables. So the right is the inertial frame. Let me zoom in. We can tell that because it says IJK. And on the table on the right, I scribbled out the IJ, I wrote B1 and B2 for the B frame, and because with the right-hand rule, K comes out of the paper, it's the same thing as B3. So K happens to equal B3. So we're going to fill this out twice. So let's start with the inertial frame. So the inertial frame was sort of simple in the sense that this omega refers to the coordinate system. It doesn't spin. Remember, the link spins, but not the coordinate system. I is always to the right, J is always up. Alpha, same thing. Angular acceleration of the coordinate system is 0. My displacement vector, we've done this a bunch of times, is R1 cosine theta, R1 sine theta in 0. But just remember, when we're ready to take our derivatives, right, R1 can stretch, so it is a function of time. So even our first set of derivatives to get the velocity from B to P, or P with respect to B, however you want to say it, is going to have both chain rule and product rule. Right now, it's pinned at B, making life easy. That's 0. Acceleration at the base is 0. Pretty easy, and as we've done countless times at this point in class, you've done for homework as well as in the review, right? I keep saying over and over again, if I can get this, these 5 lines, the rest is mindless math. Top is my worksheet. This is again my velocity at point P, or P with respect to some fixed origin, and these 5 lines to get my acceleration at P. And that's no different here. These are all the same carried through. Let's set up the body fixed, and then it's just mindless math. So this first line refers to, is the coordinate system spinning? Well, it is, because the B frame, B1, moves with the link. Depending which way it moves, it spins with the link. What axis does it spin around? It spins about K, or the B3 axis, the one coming out of the page. So it doesn't spin around B1, it doesn't spin around B2, it spins around B3. Since we're using coordinates such as theta, our variables are theta and R1, a good name for the angular velocity, still working around dead spots on my screen, would be theta dot, my angular velocity, theta dot. Similarly, my angular acceleration, to write it in general, we don't know what the problem is yet, it'd be theta double dot. Seems maybe a little bit harder, but look at my displacement vector. My displacement vector from B to P, I'll do that in red, just as a reminder, is this. Looking at the other drawing is this. So written in terms of B1, what is it? Simply R1 in the B1 direction. That's it. Some people like to write in here, it's optional, they like to write maybe of T just so they remember that it stretches. Velocity of the base hasn't changed. It does get more complex with let's say, a horizontal cut, but I'll do that in another review. You've probably already done that in class, depending when you're watching this in here. So again, 1, 2, 3, 4, and 5. The rest is just mindless math once you review your chain rule, your product rule. But now we have cross products here as well. So let's continue the one on the left. So what do we have? Well, R1 and theta are both functions of time. So if I keep the theta constant first, I would have derivative of R1 is R1 dot cosine theta. What does that mean? It's the velocity of that link, that piston, whatever it is, a hydraulic cylinder, stretching, right? How many millimeters per second does it extend or contract? That's what R1 dot is, where R1 is a length at a particular period of time. R1 dot is the velocity of its extension. Now I'm going to hold R1 constant. Derivative of cosine theta is minus sine theta. And we need the chain rule. We've done this countless times already. So I have a theta dot. And I should have units of velocity. I do. R dot is velocity. Cosine theta has no units. In the second term, R1 is length. Theta dot is radians for some unit of time, let's say seconds. So length times, let's say meters, times radians per second. You can ignore radians, so that's just meters per second, and sine of theta has no units. Easy. Let's do the next term. If I hold the sine theta constant, R1 dot, sine theta, so R1 dot again is how this cylinder, piston, whatever it is, the velocity that extends. Hold R1 constant, sine derivative sine theta respect to theta is cosine theta, and then d theta dt is also known as theta dot. And now I have that, because I have no omegas in this one. So that's it for my velocity of P. Now, for simple planar problems, it might be pretty easy. Full 3D, body fixed really becomes a lot easier than this to avoid all these like double and triple projections. Okay, let's finish this table. Omega. Get away from that area. Or 0. And now I have some derivatives to do. So just as I only looked at this line, or my R line to get my R dot, I just look at this R dot line to get my R double dot, basically my acceleration. Well, how many functions of time do I have here? Well, we haven't made any assumptions. So this is a function of time, that's 1. Theta is a function of time, that's 2. That gives me 2 terms. This one here, 1, 2, 3, it gives me 3 terms. So I have 5 terms total that I have to squeezing here. Again, you don't have to stick everything in the table. You can stick things below. And that's what I'm going to do here, or I'll never be able to write. So let me come over here. This area will be here. I'm going to have to, harder than it looks with a semi-dead screen. Try it again. Right here, I'm going to stick over there. So what do we have? We have a whole cosine theta constant, R1 double dot cosine theta. What is that? That is the translational acceleration, or linear acceleration, that this piston is extending or contracting. So let's say it's extending, 3 millimeters per second squared. Now I hold the R1 dot constant, cosine theta becomes minus sine of theta, right? Chain rule, so I have a theta dot. So those are my two terms. Now my next term, the minus R1 theta dot sine theta, will give me three terms. So if I hold the second two constant, that's easy. I get minus R1 dot theta dot sine theta. Now I'm going to hold the first and the last constant, so I get minus R1 theta double dot. So theta dot becomes theta double dot sine theta. Now I have my next term, so I hold the minus R1. Oops, I gotta move it around, sorry. Minus R1, look at it, theta dot. Sine theta becomes what? Cosine theta times another theta dot, so it's theta dot squared. So this right here, these five terms, if I didn't make any mistakes, go right in here. Similarly, since this is review, let's do the rest. Let's work on these terms right here. So just like before, the first term gives me 2. So what do I have? Other than working in the test zone, let's try it again. That might work over there. I have R1 double dot sine theta. Hold the R1 dot constant, sine theta becomes cosine theta times the theta dot. If you remember from the first review and from class, we just pick an order for the class. Some books would do theta dots before R1 dots, but this is the order that we picked. The next term in the velocity gives us three terms, so plus R1 dot, and hold the other two constants, theta dot cosine theta. Then I hold the first and third constant, so it's R1, theta dot becomes theta double dot, cosine theta. Now I hold R1 theta dot constant, cosine theta becomes minus sine, so I need to erase this plus, times another theta dot. So if I just look at this last one just as an example for my units for acceleration, and that does not work. Maybe in a future video I'll have a repaired screen. If I just look at this last term, what do we have? Move that up to a spot that does work. I have some length, let's say meters. Theta dot, remember, has to be radians per time. Let's just say radians per second. So squared, radians squared per second squared. Sine of theta has no units, so I have meters times radians squared over second squared. Radians can be ignored, so I have meters per second squared. As an example, I have acceleration. Similarly here, I have, let's see, meters and radians per second squared. And again, radians can be dropped. Here I would have meters per second, radians per second, so I end up with meters per second squared because you can drop radians. So it's always good to check your units. So that's what I have here. So again, to get my acceleration, I know most of these are 0, but it's all of these times I plus all of these times j plus all of these times k is my acceleration, and all of these I plus all of these j plus all of these k gives me my velocity. Now let's take a look at the kinematics table for body fixed. See what that looks like. So let me zoom in here. And again, so our unit vectors are b1, b2, and b3 or k is the same. So let me look here and just take a derivative to get here, and another derivative to get here. Derivative R1 dot, because it stretches. Some people, again, right of t. Easy as can be. Derivative of R1 dot, respect to time, R1 double dot. So I just have this translational acceleration. Right? Velocity is my R1 dot and R1 double dot. The rest now, as long as I remember my cross products, and hopefully you've been reviewing that. There's a couple ways to do it. I'll show you the one that I use. Remember, when we pull it out of the table, we have to put our vectors back on. So omega b cross with rp slash b. How do we use the table? First line is always whatever my unit vectors are. b1, b2, b3. Then I take my omega line. What's that? 0, 0, theta dot. Then I take my r line, which is right here, r1 of t, 0, 0. So if I take my determinant of that, let's see, if I cross out my b's, I have nothing. If I cross out my b2, what do I have? Plus, minus, plus, product this minus product of that. So I get r1 theta dot b2. Again, check your sign. I use the one with plus, minus, plus. b3, I have nothing. So in this spot here, I have 0, r1 theta dot. And again, it makes sense. It's units of velocity. Not too bad. Pause here for a moment so you can get caught up with it. All right, now let's try the next one. All right, need to work, so let me try to reset. Okay. Next line says alpha b crossed with r p with respect to b. Those are vectors. What do? Same idea. Top line is always my unit vectors, pretty mindless to set it up. This can be automated by computer. Alpha line says what? 0, 0, theta double dot. That's angular acceleration for coordinate system. And it's actually the link as well because it's body fixed. And from B to P or P with respect to B, we've just seen that R1, 0, 0. Okay, I do the plus, minus, plus. So when I get to the minus one, let's say the B2, right, it's the product of this minus the product of that, but it's plus, minus, plus. It's R1 theta double dot B2. Practice it. Come see me. Find somebody's YouTube video on it. Whatever you like. So that becomes 0, R1 theta double dot under the B2 column and 0. Next line is my omega cross r. And you can see how these things are in order. And it makes my life sort of easy. Everything is lined up. And when you get to grad school, or maybe even here, you might start automating the stuff on the computer. So we said it's omega b cross with omega b, right, these are vectors, cross rpb. Hopefully it's getting mindless. b1, b2, b3, which is the same as k. Get rid of that straight line there. Omega line, you've seen that before, 0, 0, theta dot. What's omega cross r? We found that. That was here. We've already done that. See, they're in order. 0, r1, theta dot. And then we have 0. Okay. So, b1. This minus product of that. So, I have minus r1 theta dot squared. b2, I have nothing. b3, I have nothing. Okay. So that one was b1. Minus r1 theta dot, and the b1 is at the top of the column. Last one. You also notice from a physics standpoint, when you use body fixed, things make more sense in terms of the notation because it falls in the right category, in this case for Coriolis acceleration. So what do we have? 2 omega b crossed with RPB. Don't forget that 2. You can put it wherever you like. Mathematically, it'll work out. I can stick the 2 on the outside. I can put it on the inside. I'm going to put it on the first line. I like it that way. So the omega line, 0, 0, but it's 2 theta dot. And then my R line was R1, 0, 0. So what do we have? Might be 1, the zeros, might be 2. So minus, so minus and a minus. So it's 2 R1 theta dot. Remember, we picked an order for the class. B2 and B3, 0. So 0, 2 R1 theta dot, and 0. Because remember, the B2 is on top of the column. So how do we read it? I have this in the B1 direction, so I wouldn't call it VPX, I call it VP B1. This in the B2, so VP B2. And here's my acceleration. Again, just to show you how I would mark it if I needed to move it to my next table, I would call it AP instead of X, I call it B1. This I would call my acceleration point P sub B2. This would be my B3 if I needed it. So there you go. There's a comparison between the two. Which is easier, almost doesn't matter, but again, when you get to full 3D, body fix becomes a lot simpler. If I was just doing simple planar problems like slider cranks 4 bars, I probably would stick with Inertial. Hopefully these reviews are helping.